we are going to see the fundamentals of contacts. Any contact pair has a minimum of two entities, a contact and a target. A contact geometry contains all the elements to carry out the contact-related calculations, for example, gap, penetration, or pressure. A target geometry is treated as a mathematical boundary. With respect to this boundary, status of the contact surface, in terms of gap or penetration, is predicted. An example of a contact and a target is shown in the figure below. The contact geometry is highlighted by red-colored edges and the normals. The target geometry is highlighted by blue-colored edges and the normals. Note that, in the first meshed figure, contact and the target surfaces are separated. The distance between the two is the gap. In the second meshed figure, the contact surface penetrates the target surface. Note that, in both the figures, the gap and penetration are calculated along the normal to the contact or target elements. Now, we are going to see how contact detection takes place at the contact-target interface. If the contact and the target surface elements are within a predefined distance from each other, the contact is detected at the interface. This predefined distance can be imagined as a sphere of certain radius, with origin at the contact detection points. Contacts are detected when the contact and the target elements are within the radius of the sphere. In ANSYS terms, this radius is known as a pinball radius. As you can note in the two pictures, the contact elements are defined on the entire curved surface. However, only a few elements are within the pinball radius. Therefore, the contact gap is calculated only for the few elements where the gap is less than the pinball radius. For all the other contact elements, no calculations are carried out. In the previous slide, we saw the concept of a pinball radius. The table in this slide shows different contact designations for different gap and penetration conditions between the contact and the target elements. This is known as a contact status. If the distance between the contact and the target elements is greater than the pinball radius, the contact status is designated as far open. If the contact status is far open, and the contact type is bonded, or no separation, then no constraints are created between the contact and the target elements. For frictional or frictionless contact types, no contact calculations are carried out. If the distance between the contact and the target is less than the pinball radius, but greater than 0, the contact status will be near open. In case of bonded or no separation contact type, no constraints will be created for the near open status. For frictional and frictionless contact type, only contact gap will be calculated with the near open contact status. If the distance between the contact and the target is negative, but smaller than the pinball radius in magnitude, then the contact status will be closed. For bonded and no separation contact types, constraints will be created between the contact and the target elements. For frictional and frictionless contacts, contact penetration, contact reaction forces, pressures, frictional forces, and all other relevant outputs will be calculated. If the distance between the contact and the target is negative and larger than the pinball radius in magnitude, the contact status will again be far open. No contact-related calculations will be carried out. No constraints will be created between contact and target surfaces. It should be noted that far open and near open conditions may naturally occur before or during the solution. Closed contact status is the best for getting a quick solution of the contact simulation. If the contact status is far open with very high penetration, this is an unrealistic condition. It generally indicates some incorrect contact settings, or some other FE model problems, causing solution difficulties. In the last slide, we saw how excessively high penetration in a contact pair can make the contact simulations unrealistic. The condition of ensuring preferably zero or at least a minimum possible penetration at the contact interface is known as a no penetration condition. This is essential to ensure a realistic contact simulation, as in real life, the contacting surfaces never penetrate each other. Consider a contact and a target pair, shown in the figure. Let delta be the gap between the undeformed contact and the target surfaces. Let nu C and nu T be the normal deformations in the contact and the target surface, respectively. Let F be the applied force on the contact surface, and let lambda be the separating force generated at the contact interface. Now, we can write the gap, or a penetration, between the contact and the target surface as G equals delta minus nu C minus nu T. When the gap G equals 0, the contact will be closed. To ensure that there is no penetration, contact gap G should be greater than or equal to 0. Also, the relation between the separating force lambda and the gap G is as plotted in the curve. It should meet the following condition: G multiplied by lambda should be equal to 0. To explain it better, when gap G is greater than 0, then the separating force lambda equals 0. The separating force lambda becomes non-zero when gap G becomes 0. This is a mathematical representation of a no penetration condition at the contact interface. Although no penetration is permissible at the interface, contact calculations are performed, allowing marginally small penetration at the interface. This is due to the limitations of a numerical solution. There are a number of algorithms available to incorporate a no penetration condition in the contact simulations.